Welcome everyone to my presentation at IEEE Sensors 2021. My name is Wang from Queen's University Belfast, UK. This paper reports one study in the project that is funded by UK Research Council EPSRC. This study seeks to answer one important question. Is it possible to differentiate two common types of respiratory viruses by portable NIR spectrometer coupled with machine learning? This study will inform further studies in the project. As the PI of this project, I am presenting this paper on behalf of the whole team. We are still living in the shadow of the COVID pandemic. So we know that respiratory viral infection is a serious risk to population health. COVID is a respiratory viral infection caused by a type of respiratory virus, SARS-CoV-2. There are other respiratory viruses, including RSV, SEV, influenza, and rhinovirus. Virus detection is an important means to manage a pandemic. There are many methods, including PCR, which is the gold standard. PCR is costly and time-consuming, but it is quite reliable. Alternative methods include biosensors, immunoassays, and spectroscopy. So they are typically cheaper and faster, but their reliability have yet to be established in many cases. Focusing on spectroscopic methods, we know some instruments have been reported as effective tools for the detection of some virus, including influenza, RSV, HIV, hepatitis, and SARS-CoV-2. And in particular, NIR has been reported to be effective in detecting Zika virus, H7N9, and porcine circovirus type 2. They are typically simple, fast, low cost, so they are suitable for point-of-care deployment. An important question here is, does it work for respiratory virus detection? This paper reports findings from one study, which is part of a funded project. And in this project, we study NIR spectral characteristic of respiratory viruses and design the data analysis pipeline in order to build spectroscopic virus detection models. So ultimately, our aim is to build a spectrometer-fronted cloud-based system for in situ virus detection, so which can record spectra from patient samples and then quickly return the positive negative result. In this particular study, we investigate the feasibility of using portable NIRs to classify RSV and SEV. We believe if we can do so, we should be able to classify virus versus non-virus, which is effectively to detect the virus. And we should further detect SARS-CoV-2. And this particular paper is based on a total of 440 RSV and SEV sample spectra collected over 4 sessions. And the data analysis pipeline consisting of pre-processing, variable selection, and PLSDA. Data measurement was done using the measurement system on the left. Here we have an NIR spectrometer, a light source, a computer, a probe, and the sample holder. The sample holder has a glass slide, a sample well on the glass slide, and a reflectance standard, so that the measure is relative to this standard. So in the measurement system, the most expensive equipment is the NIR spectrometer, that is from Ocean Optics. So it costed £10,000 5 years ago, but in today's price, the whole system cost no more than £2,000. And the data measurement protocol is summarized on the right. And so there are two types of virus in this study, the RSV and SEV. Virus stocks are stored in minus 80 degrees centigrade, but thawed quickly in the 37-degree water bath before use. Virus samples are diluted by tenfold serial dilution in PBS. And a tiny drop of diluted virus sample was pipetted onto the sample well of the glass slide and covered with a cover slip for measurement. 10 spectra per virus sample were collected in 4 sessions in the year 2020. In this study, we pre-processed the data before we modeled the data. For pre-processing, we used SNV to reduce the scaling differences before spectra. We used SG to remove baseline offsets. We used VS to select variables based on standard deviations. For modeling, we used PLSDA, which is the standard in chemometrics. The experimental protocol is the machine learning one. We split the data into training and testing set at a ratio of 3:1 over virus samples. In the training phase, we use tenfold cross-validation to optimize the model. Then we use the optimized model to predict on the testing set. Here we have two plots. The left is a plot of the raw data, and the right is a plot of the pre-processed data. And different colors represent different viruses. And clearly you can see they do have differences between the two viruses. These differences may not be big enough for spectroscopists, but big enough for machine learning to produce good enough results. And we will see the machine learning result in later slides. We have two plots here. The left is a scatter plot of the data using 3 latent variables obtained using PLSDA. So you can see the two classes are largely separable in this space. And the right is the loading graph for the 3 latent variables, which indicates the contributions of the original variable for each latent variable. We can see some variables are more important than others for a latent variable. This table shows the classification result in accuracy and sensitivity and the different combinations of data pre-processing methods. The first row is results using raw data only. And the second row is the result using SNV plus SG pre-processing methods. The third row is results using SNV plus SG and VS. Clearly, you can see that the third row produced the best overall result. The first column lists validation results on the training data. The second column lists prediction result on testing data. So you can see the corresponding results values are quite close, suggesting overfitting is low. So this also means that the prediction result should be fairly reliable. The third column lists RSV sensitivity values, and the last column lists SEV sensitivity values. And one highlight is the bottom right value, 0.9, which means using this combination of pre-processing, SEV sensitivity can be as high as 90%, which is quite decent using this approach. The last two columns also suggest that SEV is more sensitive than RSV using this approach. Okay, and in conclusion, And this paper presents a data-driven study demonstrating that aqueous dispersions of the two common respiratory viruses can be distinguished with a high degree of accuracy based on their NIR spectral responses. However, how to interpret their NIR spectral differences has not yet been elucidated. So that is the current focus of the project. And future work will include the following: interpretation of their NIR spectral differences, which enable their detection, and testing the analytical protocol on different viruses, including rhinovirus, influenza virus, and SARS-CoV-2 virus. So this concludes my presentation. Thank you very much.